Cop Review Assignment 1. Let's begin. Define Earth Science. Earth science, as you guys hopefully have picked up, is the study of the Earth and all of its components. So that incorporates fields of study like geology, biology, environmental science, oceanography, and even astronomy. Next, name Earth's 4 spheres. So that would be the atmosphere, the biosphere, the hydrosphere, and the geosphere. Here you see that all of them are defined, but the atmosphere, that's the envelope of gas that surrounds the Earth. Biosphere is all life on Earth. Geosphere is going to be all the solid rock, all the material that makes up the Earth. And then the hydrosphere is going to be all of the water. So whether you want to think about it that as the glaciers or the ocean, rivers, streams, that's all hydrosphere. Contrast model and system. Now I'll tell you, there's more to it than the statements that are here, but systems are how we break down the larger picture into smaller pictures. So take the human body. We don't study just the whole human body. Instead, we break it up into the circulatory system or the respiratory system. In the same way, we break up Earth into systems, and that's where we looked at meteorology and the hydrologic cycle, or we looked at the geosphere and we broke it up into the rock cycle or some other superficial processes. Models are how we actually explain what we're looking at. So models, remember, you can have a mathematical model or a conceptual model or a physical model, right? So a physical model, it's tangible. Hey, I got a model of a rocket, and outside you could actually see a whole big rocket, right? It makes it easier to explain when it's smaller and in your hand. Conceptual models, that's how we explain how the universe is expanding, or we explain concepts that you really can't see. You kind of just have to think about and go, okay, that makes sense. All right, moving along. What is the composition of clean, dry air? That should be 78% nitrogen, 21% oxygen, and 1% other. Next, the biosphere is anything that supports all life on Earth. Too easy. The open system exchanges energy and matter with its surroundings. So far, so good. Now it says to compare sunspot, solar flare, and solar prominence. Now these are nice definitions here, but how do you connect all the ideas? Well, in Earth's layer, you have the convective zone, which is right underneath the photosphere, the visible surface of the sun. Now when that convection comes up and breaks through the surface, it can make that circular pattern, which you see there, and that would make the solar prominence. So you'd actually see a spread of plasma moving through an arc pattern. But if we were to just break that and just shoot straight out, then this would be your solar flare. And that would be ejecting a lot of that material out into space. If you think about the convective cycle, though, where you have a break and where you return, those are kind of your sunspots. Those are going to be areas that are going to be a little bit cooler because the convective cycle has taken place. All right, moving along. What is the heliocentric model? And name 2 astronomers whose work provided evidence for this model. So the heliocentric model said that the sun, Helios, the sun god, so the Helios or heliocentric model, the sun is at the center of the universe, and this was first proposed by Copernicus. It was then supported by Galileo. Remember that Galileo had seen phases on Venus. He had seen that Jupiter had 4 moons. Now we know that it has 63 moons, but he saw the 4 largest moons, Io, Europa, Ganymede, and Callisto. And from that, he also looked then back at the sun, and with his telescope, bad idea. We believe he might have gone blind from that, but he saw sunspots, and he also was able to see that the sunspots were moving which prove that the sun itself rotates. All of this he put together, published, and ended up on house arrest. The last person that we want to talk about then is Kepler, Johannes Kepler, and Kepler's 3 laws of planetary motion, again supporting the heliocentric model. Now, which of the following is not a Jovian planet, not a Jupiter-like planet, not one of the big gaseous planets with rings and many moons? Oh, okay, I guess that would only leave us Mars, because Mars is the last of the terrestrial planets, Earth-like planets. You know, the rocky planets that don't have many moons and don't have rings. I think I emphasized that enough. Asteroids spend most of their time between Mars and Jupiter. That's where the asteroid belt is located, between Mars and Jupiter. Planetary orbits are elliptical. And moving right along, the life cycle of a medium mass star. Medium mass would be like our sun. So it began as a nebula, a ball of a cloud of gas and dust that then started to compress. Once it started to heat up, we called it a protostar. But the second that hydrogen fusion began, and it actually starts to emit energy, now it was a main sequence star. Once all the hydrogen is used up, the core starts to compress down, causing helium fusion. At this point, you've left the main sequence, where it spent most of its life, and now you become a red giant. The star will expand, just like our sun will expand, and hydrogen fusion goes, then you're going to have fusion all the way out to oxygen and carbon. Finally, the core starts to collapse down, compressing for what will become a white dwarf. So the core is compressing. All the gases that surround the outer portion of that star will continue to glow as hydrogen fusion and all the other energy is released. That is your planetary nebula. So it's a halo around a condensing solid core that will become your white dwarf, which eventually will lose all of its energy, and once you stop emitting all light, you have yourself a black dwarf. Good. How far is 1 astronomical unit? Folks, this is science, so we're going to talk about the metric system. It's 150 million kilometers. Right? Better be million kilometers. 150 million kilometers. Good. And that's the distance, by the way, from the Earth to the Sun. What is a topographic benchmark? This is a point of known elevation on Earth's surface that is marked with a bronze or brass placard. And when you go and find that, you know exactly what elevation you're at. On a map, it will be marked by either a BM, an X, or a triangle or delta symbol. Good. Half circle of 180 degrees of arc which connects the Earth's poles is known as a meridian, or the actual line is a meridian, but we're discussing longitude there, so meridian is the best answer. Good. Principal purpose of topographic maps is to display elevation and terrain by the use of contours, right? By the use of contours. You're showing Earth's 3-dimensional surface using a 2-dimensional map with the contour lines on there. Good. Contour interval is the difference in elevation between 2 contour lines, or as it says here, elevation between 1 contour line and the next line. List the 5 requirements to be a mineral. First off, it must be naturally occurring, meaning that it's not man-made. Must have a crystalline structure, must be solid, must be inorganic, must have a definite chemical composition. Now here, it says contrast tenacity and hardness. All right, so I don't actually like this statement after looking at it. Tenacity is resistance to breaking. Someone who is tenacious means that you can't break them. They've got will, they've got determination, right? And when it comes to your comps, you all need to be tenacious. When it comes to your studying, you better be tenacious. Hardness, on the other hand, is the resistance to scratching. And we know that with hardness, we use the Mohs scale of hardness to classify different minerals. Good. 2 examples of native elements: gold, silver. Those are real easy. Copper, sulfur, silicon, all great examples. Diamond, right? It's made of all carbon. So, those are all great examples. Describe different classifications of igneous rocks. So you can have intrusive or extrusive, also known as plutonic versus volcanic. If it's intrusive, it's going to cool slowly. It's going to be coarse-grained. If it's extrusive or volcanic, it's going to cool quickly. It's going to have smaller crystals. The other classifications that we might want to use are mafic versus felsic. Mafic meaning that you have a lot of magnesium and iron, tends to be heavier elements, darker elements. And felsic, feldspar and silicon rich, so lots of feldspar and quartz in there, and that's going to be lighter in color. Good. The diagram below is showing the elastic rebound theory. You're building up the stress between time 1 and time 2, and then snap, you get the earthquake, you get that displacement, right? Remember, strike, slip, fault is being shown here, but the actual diagram represents the theory of the elastic rebound. So when it snaps, that elastic deformation now goes back to its normal orientation, only you've had displacement along the fault. You might want to replay that if you didn't understand what I just said. Contrast focus and epicenter. The focus is the actual point within the Earth, the origin point for an earthquake where those P waves and S waves are going to originate. The epicenter is the point directly above the focus on Earth's surface. Remember that epi means surface, like your epidermis is the surface skin that you have. Well, the epicenter is going to be the surface point where directly above that focus. If you're looking at material online, sometimes they call the focus the hypocenter, and hypo just means below. So the point below Earth's surface. There you go. And then we get to our different types of waves. Here we have body waves, and body waves are the waves that are going to pass through the Earth. Please remember that. In fact, you have your P waves, the fastest moving, your primary waves. These are compressional waves. Compressional meaning that they're going to keep pushing in one direction, which is why they're going to move so quickly. Right? That's the kid that's walking down the hallway and just driving on, not getting distracted. Therefore, a P wave can go through any material or any medium, so solid, liquid, or gas. It does require a medium, by the way. S waves are shear waves. They go side to side, and they're only going to be good for going through solids, because the second they try and go into a liquid, when they start going side to side, well, they start to swoosh and lose their energy. They get lost. And that's that kid that never really makes it to class because they keep walking side to side to side, moving across the hallway, not moving very quickly. Therefore, let's go back to the idea that P waves are the first ones to arrive. The S waves, there's always going to be a delay in that arrival. And that difference between the P wave and the S wave is known as lag time. Please recall that lag time is going to be necessary for figuring out the distance from the epicenter. The greater the difference between those two times, the further you are from the actual epicenter. Good. Define shadow zone. And shadow zone, we actually have 2 different types. We have a P wave shadow zone, which is going to be along the sides over here. This is where you're not going to get any P waves, but this whole area back here, this great circle, you're not going to get any S waves. So where we say that you get no P or S waves, right here and right here, that's going to be your major shadow zone. You're not detecting any earthquake. And the reason you don't get any S waves, again, is because S waves cannot travel through the liquid outer core. The reason you can get some P waves on the opposite side is because due to refraction, as the waves pass through the different layers of the Earth, the P waves will bend, and sometimes they can actually bend and you'll be able to detect them on the opposite side. But just think, shadow zone, no waves making it to the seismic station. You're not picking up on the earthquake, and the primary one for that, or the main wave that you're not going to be detecting, is the S wave. That's the big focus there.